All right, so up to this point, we've done in class, we've done conservation of energy problems without any friction involved. So this time, let's do an energy problem with a non-conservative force, and by that I mean that friction is present. So let's say here's the problem. So we're going to go skiing, and we're going to go down this 300-meter long hill, which has an angle of 10 degrees. And we have the following information. We have the mass of the person being 100 kilograms. The starting velocity of the person at the top of the hill is 0. The coefficient of kinetic friction between the snow and the ski blades is 0.1. And just for ease of math, let's make our acceleration of gravity 10 meters per second squared. All right, and the goal of this problem is to find the final velocity at the bottom of the hill. All right, so let's go through the process of solving this using what we know about energy. All right, first we're going to draw a little free body diagram on our character. Beautifully drawn character, by the way. Right, so we've got the force of weight, and we have the normal force, right. We also have the weight in the x direction, right, and we have the weight in the y direction. And if you recall, the weight in the y direction would be equal to the normal force in this case. All right. Also, we happen to have friction, right? So we know that friction is going to act along this entire length of this ramp, right? But it opposes the motion, right? So we know friction is going to act in this direction. All right, opposing the motion. All right, so let's figure out some values of forces. All right, so again, since we were going to make G be 10, all right, we know that the force of weight, 1,000 newtons. I'm not going to worry about sig figs on this too much. All right, so if we figure out the components of the force. All right, so we have the x component of the force. That would be the weight times the sine of theta, and the y component would be the weight times the cosine of theta. All right, and in reality, in this particular problem, we're not going to need to know the x component of the force, since we're just going to work with energies. So no need to worry about that. But we do need to know the y component, because ultimately, right, that equals the normal force, and we need to know the value of the normal force, right, because ultimately we have to find friction. All right, so if we plug in our numbers, right, we know the weight is 1,000 newtons, right, times the cosine of 10 degrees. Right. That'll equal 985 newtons. Right. And then also to figure out our force of friction, right, that's the coefficient times the normal force. Right. So in our case, the coefficient is 0.1. And the normal force is equal to the y component, right? So this is the normal force. So 985. And we end up with 98.5 newtons. All right, so that's the basis of this problem. Here's what else we know, right? We know at the top of this hill here, that we're not moving. But we are going to need to know the height of the hill. So we need to know this up and down height in order to do the problem. All right, so I know the length of the hill is 300 meters, and I have a 10 degrees. So we do a little bit of trigonometry to figure out the height, right? So for the height, we could take the hypotenuse times the sine of the angle, because we're opposite the angle, right? So in our case, that gives us the height to be 52.1 meters, right? That number is going to come in handy when we start using our energy equation. All right, so let's look at our energy equation now. So ultimately, right, we're trying to figure out at the very bottom here, when we get to the bottom, how fast are we going? All right. All right, so let's do a little bit of sidebar. Okay, so let's use our energy equation to get this problem started. So we know that the total energy in the beginning plus the work non-conservative will equal the total energy at the end. All right. Now the energy in the beginning is the sum of our mechanical energies. So we have kinetic and we have potential energy. Right. So if I take the potential energy initial plus the kinetic energy initial, and we look at the work non-conservative, right? So in our case, the work non-conservative, this is over here, the work non-conservative would be the force times the distance. But the force that we're talking about is the friction. So the friction is causing really heat as we go down here. So really the friction is stealing some of our energy. So we're going to make that negative or subtract out the work non-conservative. So if we apply that to the equation, minus the force of friction times the distance. So that takes care of this left side of the equation. Now we have the right side of the equation. Right, we have the potential energy final plus our kinetic energy final. Right, and if you recall, right, potential energy is mgh, and kinetic energy is 1/2 mv squared. All right, so let's substitute in. So I have mgh initial plus 1/2 mv initial squared minus force of friction times the distance. Then we have final potential energy, mgh final, plus 1/2 mvf squared. All right, so again, we are looking for our final velocity at the bottom, right there. Let's do a little bit of logic. So we know at the very bottom of the hill, right, our height will be 0. So that means that this part of the equation disappears. And we know in the beginning our initial velocity is 0. So this part of the equation disappears. So we're left with a equation that's a little bit easier to handle. All right, so let's, at this point, we could probably just substitute numbers in and then start simplifying. All right, so if we substitute numbers in, we know mg is the weight, right, which we already figured out to be 1,000 newtons. Right, we figured out the height to be 52.1 meters. Okay. Force of friction, right, we figured that out earlier, right, that's 98.5. The distance that force of friction is going to be applied is over the 300-meter length of the hill. All right, that takes care of this side of the equation. Then we have 1/2 of the mass, which was 100 kilograms, VF squared, which is what we're looking for. All right, let's do the math. All right, so multiply these together. You get 52,100 Newton meters minus 29,550 Newton meters equals 50 kilograms times VF squared. All right, so VF squared equals the 52,100 minus the 29,550. That works out to be 22,550. Let me correct that. $22,550, and we're going to divide by the 50 kilograms. That gives us 451. Right, and we got to take the square root of that. So VF would be the square root of 451. And that equals 21.2 meters per second at the bottom of the hill. All right, so what makes this a little bit more unique is the fact that we lost some of our energy due to the friction, which creates heat. All right, so final answer. Good luck.